Check, check. Excuse me, guys. I'd like to request that all of you settle down. Yeah, I'd like to request all of you to settle down. The event is starting now.
Good afternoon, everybody. It's a great honor to welcome you all to the ICTS Einstein Lecture, hosted here at the Peers University in association with the International Center for Theoretical Sciences, Bengaluru. We are truly delighted to have an esteemed professor amidst us, Professor Scott A. Hughes from the Massachusetts Institute of Technology, US of A. A very warm welcome to Professor Scott. Thank you for your presence, sir. Professor Scott Hughes is a professor of physics at MIT and Margaret McVicar faculty fellow, currently serving as interim associate departmental head. He has earned his BA in physics from Cornell University and his PhD in physics from the California Institute of Technology, where he worked under Nobel laureate Kip Thorne. Before joining MIT in 2003, he held postdoctoral positions at the University of Illinois, Caltech, and the Kavli Institute of Theoretical Physics at UC Santa Barbara. Professor Hughes' research explores astrophysical general relativity, focusing on black holes, gravitational waves, and strong field gravity. His pioneering theoretical work has played a key role in shaping the field of gravitational wave astronomy and in advancing experiments such as LIGO, which achieved the first direct detection of gravitational waves. In addition to his research, Professor Hughes is a dedicated educator and science communicator. He was named a McVicar Faculty Fellow in 2017 and is a Fellow of the American Physical Society and a John Simon Guggenheim Fellow. On behalf of the management of Peers University, on my personal behalf, and on behalf of all the enthusiastic students out here, and on behalf of the organizing committee from Quantum Forest, the student team which is organizing this particular fantastic lecture, a very, very warm welcome to Professor Scott Hughes. I take this opportunity to also welcome Dr. Ajit Parameswaran, the Dean of the International Center for Theoretical Sciences, who is also an astrophysicist. He has been instrumental in facilitating the visit of Professor Scott Hughes to the portals of Peers University. A very warm welcome to you, Ajit. Thank you. I also have the pleasure of welcoming all the deans, chairpersons, and the professors from Peers University, and also all the I think the mic is telling me, shut up. All the professors and research scholars and students from various institutions who have come here to listen to this wonderful lecture by Professor Scott. It's over to you, Scott. Looking forward. Thank you.
Thank you very much. All right, well, thank you for that very warm introduction. I have the slides back up. There we go. Okay. So thank you very much for this, like I said, for this very warm introduction. It's wonderful to be here. I have been in India for 15 hours so far, of which I've spent about 6 of them asleep. So I'm a little bit jet lagged. I am running on enthusiasm, sugar, and caffeine, and I hope it will last for the remainder of this hour. I think it will. So reason I have so much enthusiasm and where I'm getting the energy to make up for my lack of sleep is that I have a story to tell you that has been the center of my career. I think it's one of the most wonderful things humanity has achieved over the past decade or so. And it's all about learning a new way of observing the universe. How have we developed this form of astronomy? And I think my pointer is off. There we go, let's try that again. It's worth noting that up until about a decade ago, whenever we observed the universe, all of our observations were based on light. Okay, we looked up into the night sky for thousands of years and looked at the stars, and that gave us a sense of wonder. It gave us a sense of curiosity about what was out there. Galileo came along and taught us how to use our eyes a little bit better. And we developed technology to bring those stars a little closer to us, to explore them even more deeply. As we learned more, we began expanding the spectrum of electromagnetic radiation that we could look at. So I have an image here of the Giant Meter Wave Telescope, which actually plays a role in some of the science I'm going to talk about a little bit later in this talk. The Chandra X-ray Observatory gave us amazing images of the universe, and they still are today, and from high-energy photons that we can observe, all the way to the current measurements that are being made using the James Webb Space Telescope. There is an amazing story that has been put together using all of these observations. But what we've learned is that this is not the whole story. All of these things can be thought of as essentially augmenting the capability of the human eye. The human eye is an amazing thing, the human eye and really the human brain put together. But we have learned recently how to observe the universe using gravity. And one of the stories that I want to tell you about this is that we don't really think of this, what we learned from gravity, as augmenting our eye. What gravity has given us is a way of understanding the dynamics of sources, which is much more akin to what we pick up with our ear. This is a gravitational soundtrack, and that's the story that I want to tell you about over the course of the next 50 or so minutes. To lay this out, I need to give you the full story of gravity. So, if I go really far back, a prehistory of gravity, where we began to think about what we now understand as gravity goes back to our first study, looking up at the sky and wondering, and thinking about what is going on when we look at various objects with time over the sky. And at least within European civilization, the first documented codification we have of this comes from the Greeks, who told us that the sky had two main constituents, the asteria, or stars, that were fixed, and the planetes, the wanderers, whose positions changed with time. This was all described in Ptolemy's Almagest, a 2nd century codification of everything that was known then, and it taught us that the universe consisted of the Earth at the center of everything, stars that were fixed and resided on a celestial sphere that we could observe, and then the planets are on other little spheres that sort of wandered around in between them. We sort of would say, when you look at them, sometimes the planets would move this way, and then they would stop in reverse direction and have this epicycle before they would start moving forward again. I emphasize this because often these days, when you hear people talk about these epicycles, the sort of description of planets that go back and forth and do things like that, we kind of think, those silly ancients. They didn't know what was going on, and we kind of sneer at them a little bit. But I want you to look at some data. This is the position of Venus in the sky with a picture taken at the same time every night with respect to those stars. That sure looks like something that moves, then reverses direction, and then goes back. So don't sneer at these epicycles. That was a fine description of the data. And all you can do when you develop a theoretical system to describe what you're observing is come up with something that does a good job describing what it is. Maybe you'll do better later, but if you've got something that does the job now, go for it. And that's essentially what I think when I look at these epicycles. Now, indeed, we did eventually realize that we could simplify this. We could actually get rid of these epicycles by demoting the Earth. Instead of having the Earth at the center of everything, we put the sun at the center, and we put planets in orbit around it, and we make the Earth just another planet. That was somewhat controversial, because this was one of the first times when, especially within the religious doctrine of Europe as it was laid out at that era, we were demoting the role of humanity. People weren't that happy about that. But indeed, further progress came from the fact that the sky was providing us with data. And so in 1572, there was a nova stella. If you know your Latin, that means there's a new star that appeared in the constellation of Cassiopeia. A new star is an oxymoron in the whole framework that had been codified by the Greeks and handed down to us through the writings of Ptolemy. So people looked at this and it's just pandemonium reigning. We're putting the Earth, it's just a planet, the sky's changing. What can I count on now? Well, pardon me. If you really want to move forward, you need more and better data. Data is always the answer when you are trying to understand something. Go out and observe. And some of the best data for this came from an eccentric Danish nobleman named Tycho Brahe, who spent a good chunk of his fortune when he wasn't getting angry with his neighbors and getting into duels and causing horrible chaos in the social circles of Danish nobility, he stared at the sky. And what he did was he very precisely cataloged things that he measured there. So it's not just enough to look at things, you need to record it, you need to be careful about it. Based on these data that he took, his assistant, Johannes Kepler, studied and realized that the planets could all be described using a very simple set of laws. Indeed, we needed to put the sun at the center, just as Copernicus said, but the planets aren't moving on circles, they're actually moving on ellipses. And when you do that, you find that the planets move with a law that tells us, so if you imagine that there's a string that connects the planet to the sun, the amount of area that is swept out by that string as it moves around the orbit, it covers equal areas in equal times. Those of you who are physics students will later learn that there's a way that we can describe this that's even more precise and quantitative, but this was enough for us to get a better theoretical description of what was going on. And we also found, when you looked at the data, that the square of the orbital period, so let's say Earth takes 1 year, so 1 squared is 1, is proportional to the cube of the semi-major axis of that ellipse, basically how big the ellipse was. So in the units we like to use, the Earth's orbit has a radius of 1. 1 cubed equals 1 squared. That's an equation that we can all live with. Okay, but you look at another planet, its orbit might take 2 years. So you square that 2 years, and the semi-major axis of that thing will be the cube root of 4. And this law described all of these planets. Isaac Newton came along and was able to describe where all of these empirical laws that just were a way of describing the data, the way it actually came together. He showed that these were all due to a universal law of gravitation, which simply states two objects are attracted by a force proportional to the product of their masses and inversely proportional to the squared distance between them. This was perhaps the greatest revolution to come along in Western science. And as I was doing my research for this talk, I realized there was a missed opportunity here. Because, in fact, this concept was actually introduced by the Indian philosopher Brahmagupta well before Newton came along. So Brahmagupta is best known for introducing the notion of zero to mathematics, but he also put together something which I'm not going to attempt to pronounce the Sanskrit, but he put together a notion that essentially says that objects fall on the Earth due to a force of attraction by the Earth. The Earth, constellations, okay, it's a little off there, but the moon, the sun, they are all held in orbit by this attraction. This was 1,000 years before Newton came along. So if we had been paying attention, I think we could have refined this and actually turned this into something that would have brought this revolution along even earlier. Well, Newton nonetheless gets credit for making a quantitative statement of gravity that serves as the foundation to everything that we use in our science up to that point. It gave us a description that accurately told us how objects fall near the Earth's surface, tells us about the orbit of the moon around the Earth, orbit of the planets around the sun, and in some ways, even more impressively, given the sort of relatively primitive state of observations at that time, these moons had recently been discovered orbiting around Jupiter, and it worked for them as well. It was an absolutely universal law that described every phenomenon that could be observed at that time. So this was in the 1600s, and it led to Newton being celebrated by many people in culture then. And so Alexander Pope, a famous essayist, wrote, "Nature and nature's laws lay hid in night. God said, let Newton be, and all was light." It did not last. The devil howling, "Ho, let Einstein be," restored the status quo. So this is where the situation gets interesting. Newton's laws indeed work extremely well, but it became clear over the course of centuries that they didn't quite work for Mercury. When you look at the orbit of a single planet around the sun, you indeed get an ellipse, as Kepler's laws demanded. But our solar system doesn't consist of the sun and just one other planet. There's a whole lot of other planets, depending on when you learn the planets, either 9 or 8. So when you include the influence of these other planets, that ellipse doesn't just sort of go around forever. It's like you've got an ellipse, but the orientation of that ellipse is slowly changing with time. Understanding that and seeing whether that might be the cause of why Mercury's orbit didn't quite work ended up becoming a major project of what were called in the 19th century natural philosophers and mathematicians. And so they developed an entirely new field of mathematics, perturbation theory, in order to describe what happens to the orbits of a planet like Mercury when it's influenced by other planets like Venus, Earth. Mars is not so important, but Jupiter turns out to be quite important. And so what they showed was that the orientation of this ellipse would change by 5,556 arcseconds per century. So let me put that in somewhat human terms. There are 3,600 arcseconds in a degree. So this is roughly a degree and a half. 5,556 arcseconds is roughly, so if you're looking at an old-fashioned analog clock, like I have on my watch, that is the angle that the minute hand moves in 15 seconds. Okay? So this is saying that over the course of a century, we expect the orientation of Mercury's orbit to change by the same angle that the minute hand of a clock makes in 15 seconds. When you go out and you measure it, you get 5,599 arcseconds per century. It's off by 43. I'm a theorist. I look at numbers like that and I go, ugh, come on, you just must have made a mistake, okay? 43 arcseconds, if I compare that to this, again, take your watch, take your old analog clock. 43 arcseconds is roughly the angle that the hour hand moves over the course of 1.5 seconds. Okay? That is a tiny, tiny angle. Nonetheless, they persevered. It became clear over the centuries that this was something that was measured very, very accurately, and no one was quite sure what could be the cause. Well, in the meantime, Albert Einstein came along and reformulated all of the laws of physics using his principles of relativity. There's a lot that can be done here. Notice it took him 10 years to put all these pieces together. If you want to learn the details, you can spend about a semester or two of advanced graduate PhD levels studying this. But I can tell you the punchline comes from two major rules. First of all, the one equation in this talk that I know my mom would know, E equals mc squared. Mass and energy are equivalent to one another. So that means that all forms of energy gravitate just as mass does. Okay, so I drop a mass, it falls towards the Earth. But it also tells me that that gravity should be having an impact on the beam of light that's coming out of this thing, because that light is energetic. Einstein also told us that the speed of light c is a universal limit. No information or signal can travel faster than c. So this was a major input to Einstein's restructuring of how we think about gravity. Getting the details right, like I said, that takes a little while, but I can tell you that our understanding of what it means is not that hard to understand. So the impact of gravity on energy is simple to understand. So among other things, it tells us that light must respond to gravity. So what this means is that if you take a beam of light and you point it up to the ceiling, it's a little bit redder up there at the ceiling because it's climbed against gravity than it is down here at the end of my laser pointer. Can you all see how much redder it is up there than it is down here? Okay, that's a trick question, because what you are actually measuring is light that bounces off the ceiling and goes into your eyes, and so it came back down, and it actually got the green put back in by moving with gravity. If you got up on a ladder and you went up there, you would be able to tell that it was slightly redder than it is here. You would have to be able to measure things with a precision of about a part in 1,000 trillion, but you could do it. Indeed, the fact that this is true is something that I would guess just about everyone in this room has used at some point. If you do not correct for the fact that light loses energy as it travels in a gravitational field, the global positioning system would not work. Okay? It would actually degrade by an accuracy of about 8 meters per minute. It's a huge effect when you talk about something that moves from the surface of the Earth to satellites at the altitude of the global positioning system satellites. So one of the first things Einstein did with this was he took his new laws and he applied it to the orbit of Mercury. And what he found was that there's an additional term arising from all this new physics that augments the rate at which these ellipses wander. So it turns out to be something that involves the mass of the sun, the period of the orbit, the eccentricity of the orbit, the width of the orbit, the speed of light. It's just a whole bunch of numbers you kind of have to put together. Now, bear in mind, when he did this calculation, it was 1915. There were no calculators, there was no computers, and so actually doing the arithmetic was non-trivial. But he was smart, so he put all these things together, and when you turn the crank, what you find is that this term gives you exactly the historical discrepancy. In a letter that Einstein wrote to his friend Paul Ehrenfest, he said that after doing this calculation, I was beside myself with ecstasy for days. When I first read this quote, my very first thought was, what a nerd. I have to confess, though, that a few years after I first read this quote, I saw some data, after which I was beside myself with ecstasy for days. So I've learned to move past that. Now, one of the other things that is in Einstein's reformulation of gravity is this idea that no information can travel faster than light. What this means is that information about gravity must be transmitted instantly. If I have two stars that are separated by a great distance, and one of them moves, the other star immediately knows about the position. That contradicts the rule that information must travel at most at the speed of light. This, in fact, is something that we have understood for a while, not from gravity, but from electrodynamics. When you take a physics class and you study electricity and magnetism, one of the first things you learn is about the force law that arises from a point charge. And it sort of spreads out evenly in a spherically symmetric fashion. Now, if that point charge is made to move, you change the orientation of those field lines a little bit. So what this means is that if I start with something that's at rest, and then I make it go into motion, there is a shell at large radius that doesn't know it has moved yet. And there's a region on the interior that does know that it's moved. It's the join between the two of them that things look weird. It sort of puts a kink in the electric field here, and that is telling me that there has been an acceleration. That kink ends up flying out at the speed of light, and it corresponds to radiation. That is the way every iota of light that you are looking at with your eyes, this is how it is generated. It's by charges that are accelerating and making electric and magnetic field lines that have this little bloop in them. Now, the same thing has to show up with gravity. Right now, you are all gravitationally attracted to my fists, okay? My fists aren't moving, so it's just a static force. But if I start going like this, the forces that you are feeling from my fists are changing. And what you would find if you analyze that very, very carefully is that the way in which the variation in that gravitational force shows up, it kind of looks like a tide. It's sort of a force that stretches along one axis and squeezes along another. So if I want to measure this radiation associated with gravity, it's easy. All I need to do is set up some widely separated masses and look for their positions to oscillate when one of these gravitational waves comes along. So let's say you want to do that. Okay, you've got it all worked out, and you say, all right, I'm going to ask for some money to build an experiment to build this thing. Good luck. The first thing you should do is you should say, can I actually measure this? How big of an effect is it going to be? Well, when you do this, what we find is for the sources that are most likely to actually generate strong gravitational waves, strong, mind you, this oscillation here actually corresponds to 1,000th of the radius of an atomic nucleus for every kilometer of separation of my masses. So you might go to your funding officer at your favorite science agency with this proposal, and they might go, yeah, good luck. Why don't you try to come up with some other way to prove that this thing is something that we might be able to measure? Fortunately, just as light carries energy away, these gravitational waves carry energy away. So if I consider two dense stars that are orbiting each other, a binary star system, they're going to generate gravitational waves, which will carry energy away from the system. And so with time, the stars will fall closer and closer and closer together. Maybe, rather than trying to detect these things directly, going to my funding officer and looking to make a device that can measure this tiny effect, maybe I can see this indirect effect. Well, we got lucky. In 1974, people discovered a binary pulsar, so a highly magnetized neutron star. It's about 40, so it's two neutron stars actually, each about 40% more massive than the sun, but crammed into a ball with a diameter of about 25 kilometers that are orbiting each other. One member of this binary, do this carefully, one member of this binary is a pulsar. That means it sort of is a thing that gives out a very regular radio pulse. And it is so precise that it actually works almost as accurately as an atomic clock. So if I put a clock in orbit like this gives me a tool for very precisely mapping out the properties of these orbits. And I gave away the punchline by accidentally double-clicking here. What we saw by watching this system we've been watching it since 1975, is that the stars, the orbits of these stars were indeed losing energy, and the stars were falling towards one another at a rate that is exactly matching what general relativity, Einstein's theory of gravity, predicts for two stars radiating gravitational radiation like this. This was an amazing result. One thing which I want to emphasize for those of you who know a little bit about how science is done, the blue curve here is not a fit to these data. What is done is take the data at any one of these points, use it to make a measurement of the masses and the separation and the periods of the binary there. It then predicts what it will be at all other times. So that curve is actually something that just passes through all of them without any data fitting that has been done to that, other than just to determine the parameters of the binary from one data point. This ended up being something that won the gentleman who discovered this the Nobel Prize in 1993. Coincidentally, just when I was beginning my PhD thesis. And so that emboldened a lot of people to say, you know what, we can go ahead and directly detect these things. So notice the timeline here. So my colleague in 1972, Rainer Weiss, he was an ornery guy. He didn't like hearing no. And so when he was told, you know what, this looks impossible, he sort of was like, forget it, I'm going to figure out how to measure these things anyway. So in 1972, when I was 1 year old, he actually wrote this paper that examined how one can do this kind of a measurement using laser interferometry as a technique to very precisely monitor the positions of these widely separated masses. He concluded that if the lasers are powerful enough, and if we can control other noise sources, that this would be possible. Not with the technology they had then, but it defined a technology development program that people then proceeded to pursue for the next 40-odd years. The basic idea of this is that you take very pure laser light and you send beams of it down perpendicular arms, bounce them off of mirrors, and then you recombine them. It being very pure is important here because light is, of course, an electromagnetic wave. And so if you can make it almost a pure sine wave, when the wave goes down these two arms and it comes back together, you design it in such a way that when they recombine, if the length of the arms is just right, you get destructive interference and you measure no signal at this measurement device here at the end. But if something, like say a gravitational wave, wiggles those masses a little bit, you're going to get a little bit of a signal. And what Ray showed was that by having precise enough control over the position of those mirrors and an intense enough laser, you can actually measure shifts that are trillions of times smaller than the wavelength of the light itself. That is the concept that underlies the Laser Interferometer Gravitational Wave Observatory, LIGO, which has two sites, one in Washington State in the west coast of the US, one in Livingston, Louisiana, essentially in a swamp in the US South. These arms are actually 4 kilometers long, and they are sensitive to waves that are in a band ranging from about 10 hertz up to 1,000 hertz. We'll come back to the significance of that in just a second. These are not the only instruments. It's useful to have more than one. It's not just useful, it's necessary, because you want to be able to protect against random noise. And as we're going to learn in a couple of minutes, when you have multiple detectors, it helps you to learn things about the source once you've actually made a measurement. These are not the only ones that are in existence. There is another detector operating in Pisa, Italy, in essentially exactly the same frequency band. It began operating in 2017 with very high sensitivity, and it's now continually running with the LIGO detectors. We'll talk a little bit about what we've learned with it in just a few moments. And recently, a detector in Japan, Kagra, which is in the Kamioka Observatory, it's basically a mine, It also has 3-kilometer arms. It's not quite as sensitive as LIGO and Virgo, and it's being used really as a test bed for some advanced technology. But these are all instruments that are contributing to the measurements that I'm going to talk about in just a few minutes. First, we need to talk a little bit about how do we produce gravitational waves. So this is my PhD supervisor from about 15 years before I met him, when he still had red hair. He developed a research program. He was one of the leaders in developing a research program to understand in great detail the properties of waves and their sources to help us guide the analyses and measurements we would do with these, with the measurements we were planning to do. One of the things that pops out of this analysis is that your best sources are going to be things that are very massive, very dense, and moving very, very rapidly. Perhaps the best source you can possibly imagine putting together is a pair of black holes. There is nothing more massive and dense in the universe than a black hole. So if you can somehow put 2 black holes together and make them orbit each other, that would in some sense be the ideal gravitational wave source. It's also an opportunity because black holes have a very special structure. One of my scientific heroes wrote, "In my entire scientific life, extending over 45 years, the most shattering experience has been the realization that an exact solution of Einstein's equation of general relativity provides the absolutely exact representation of untold numbers of black holes that populate the universe." This was stated by Subramanian Chandrasekhar in a lecture he gave in 1975. I had a chance to meet him once before he died. He's a wonderful man, amazing scientist, but he was also clearly a theorist. Okay? This shows great confidence that the equations correspond to what nature is telling us. Can we test this? Is this faith in the structure of black holes correct? This is one of the things that drives a lot of the kind of work that people like Professor Ajith and myself think about. Gravitational wave data, because black holes have such a unique structure within general relativity, gives us a way to sort of probe whether that's the case. In particular, black holes should only be described by 2 parameters, their mass and their spin. If I have 2 non-spinning black holes, they form a binary, they orbit each other, they lose energy due to gravitational radiation. As they lose energy, they get closer together. When they get closer together, they move a little bit faster. By moving faster, their wave is somewhat stronger and at a higher frequency. And you get this shape that we call a chirp associated with these things. Now remember, LIGO is sensitive to gravitational waves in a band from about 10 hertz up to about 1,000 hertz. That is exactly the sensitivity band that the human ear has to sound. So early on in the process of thinking about these things, we began realizing that it would actually be pretty useful just to get some insight as to what the sort of characteristics of these waveforms are like, to take, this sort of, great, it's a sine wave that goes wee. Okay, what if I turn that into a sound? Let's try it. Hello? Oh, no. So the audio appears to be messed up again. Has the audio been turned off? Could you turn the volume up a little bit? Yeah, I can hear it. It's been turned down a little too much. Okay, is someone... Earlier when we were testing this, it was quite loud, and so I think they made an adjustment. I think you may have over-adjusted. Let's try this again. Okay, there's a little bit there. All right. Sorry about that, everyone. Let's try that again. Okay, we had this working earlier. Can someone, I can hear it at very low volume. Yeah. Try it again. Okay. Can anyone hear a very quiet little thing there? So whoever's got their hand on the volume knob, could you knock it up just a little bit, please? Okay, I'm hoping you can turn it up a little bit more at some point. No one's telling me if that's possible, but what you should be hearing, and I think you can hear it if we're all very, very quiet, it's just a little, okay? And so what you're hearing there is the fact that as the signal moves along, the amplitude and the frequency are getting steadily higher, so it's moving to higher frequency and louder volume. Let me do it one more time. Okay, so I think this may just be a little bit of a quieter signal in this system. Imagine now, so those were two black holes that are non-rotating. Now I'm going to make those two black holes spin. Black holes are characterized only by their mass and by their spin. So spin is the only other thing that I can do with them. Notice, in this waveform here, there's a lot of additional structure. What's going on here is that in general relativity, remember, all forms of energy gravitate. So if I have a spinning body, that spin contributes to the gravitation. And indeed, what you find when you look at this is that they kind of interact with each other like two magnets. Okay, so you end up with some really interesting forces that depend upon the orientation of the spins, and they can vary. They can sometimes make the gravity stronger, sometimes make the gravity weaker. And that causes both the frequency and the amplitude to vary over the course of the orbit. So everyone, let's try to play this sound. Let's be very, very quiet. Okay, I apologize for the low volume here, so I will do my personal encoding of this. What you should have heard just then is the thing goes, okay, so that difference, the sort of versus that is instantly encoding the difference in the structure of these two black holes with respect to one another. Thinking about how we can tease that kind of information out, that's a lot of what the science of this is all about. If I have two black holes that are very massive, what happens is all of the frequencies shift lower and lower in the same way that a very big bell has a lower frequency than a very small bell. And what we find is that there's some really rich information at the very end when these two black holes collide with one another, which is present in the waveform. Let's see how well this one plays. Okay, quiet, we can definitely hear this. Basically, it just sort of goes, boop. Now, these modes are actually called the ring down because they have the same mathematical structure as the ringing of a bell. It is a terrible bell, though. It is a bell that only rings for a couple of cycles. And so it almost, a colleague of mine likes to say, they don't ring, they thud. So this sort of final thud, which actually sounds a little bit more like a pop, is the signal that we listen to for the more massive systems. All right, so fast forward to the year, month of September in 2014. What we found was that LIGO was just beginning to go into science mode. It had just been upgraded, had much better sensitivity. Everything was sort of making sure it was all working right, and what they found was that it was just giving us essentially sort of the hiss of noise. It's exactly what you expect the system to be doing when there's nothing going on. All of a sudden, something hit at 9:50 Universal Time. So colleagues who were online in Europe at this time, they actually were on, they were looking at the data. Most people in the US, where the detectors are located, were asleep. But those who were in Europe suddenly saw this signal hit. Okay, and again, the sounds, unfortunately, are very suppressed. But what I want to emphasize is that the sound that came out of that was very much like that pop that we got from the more massive black holes actually merging with one another. It coincided almost identically to a system where what you're picking up are those final ringing modes of two black holes colliding with one another. Now, Ajit was actually in the collaboration when this happened, so he probably knows a little bit more of the details than I do. But basically, everyone went into lockdown and then spent months trying to figure out what this was. Was this actually an event? Was it someone who actually hacked the system and embedded a signal into there to try to mess with all the poor LIGO scientists? And indeed, after a while, it was concluded that what this data revealed is you have two black holes, one of 29 solar masses, one of 36 solar masses, that merged and left behind a black hole of 62 solar masses. Now, again, a little bit of math that I think we can all do. 29 plus 36 does not equal 62. In the course of doing this, 3 solar masses of rest energy actually vanished. It was converted into radiation. In approximately 0.2 seconds, the equivalent, the E equals mc squared, where m was 3 times the mass of the sun, just vanished. If this had been light, it would have shined as brightly as 175 billion Milky Way galaxies. Because it's gravity, which is the weakest of the fundamental forces, instead, these little test masses moved by a fraction of an atomic radius. But we were able to pick it up. And this was a very celebrated event. Now, before moving on, I just want to make a remark, because not that long ago, so Kip Thorne here in the middle, he was my PhD supervisor. Ray Weiss was my colleague at the Massachusetts Institute of Technology, and he just passed away a couple of months ago. And I just want to memorialize him for a second. He was an absolutely wonderful human being. And so in addition to being an experimental genius, he made contributions to developing highly accurate atomic clocks. He contributed to our measurements of the cosmic microwave background, as well as inventing gravitational wave observatories. He was a mentor, and more importantly, really a friend to multiple generations of scientists. Every time I saw him, before he asked me what I was interested in and what I was working on, the first words out of his mouth were, "How's your daughter doing?" Always wanted to know about family, how people were doing, things like that. So he's already deeply, much missed. He's been long loved and much missed. So I wanted to spend a moment to memorialize this wonderful human being. LIGO has continued to run since those first things, and it's been joined by the Virgo detectors and the Kagra detector, and there are now several hundred events. When these detectors are operating properly, we are measuring a binary black hole merger every couple of days, several per week. The universe is apparently filled with black holes, and these black holes like to smash into each other. I want to just talk, so this basically reset our knowledge of black holes in the universe. So the red dots are essentially all black holes that have masses similar to the masses of stars that we had discovered and carefully characterized using X-ray and optical telescopes. The blue dots are all the ones that we have characterized using gravitational waves. 10 years ago, this plot didn't exist. So we have completely almost increased our knowledge of the number of black holes in our universe by about a factor of 10 in that time. I want to spend one moment. There's a recent event which I think is really cool, and it illustrates the fact that the experimentalists who build these devices have not been sitting still. So there was this event measured in January of 2025, which when you look at it, so this plot that I'm showing you, the top event, the top data stream, that is the first gravitational wave that was detected. The one just below it is this event from January of 2025. It's almost identical. The parameters are very, very similar, but the noise in the instrument has been reduced by a factor of about 4, because no one's been standing still. They've been making these measurements better. And so this has enabled us to really, first of all, we've reduced these error bars, and we've been able to measure the spectrum of what's going on at the end of this thing in much more detail. And that's enabled some cool stuff that I don't have time to talk about, but I'll be happy to talk about in questions afterwards if anyone's interested. We also picked up something else that's really interesting. So in August 2017, there was a gravitational wave detected that lasted for about 1.5 minutes. Now, a signal that is very slowly evolving like that tells you that it's something that is of relatively low mass. And indeed, at the end of this event, something went boom in the sky. Detectors, 1.7 seconds after the end of this event, there was a flash of gamma rays that was seen. And so telescopes started looking at the location in the sky that the gamma ray telescopes and the gravitational wave instruments said the event probably happened. And they found a galaxy that looked like this from data that dates to sort of around 15 years ago. And then it turned into this on that day. Notice there's an additional spot near that galaxy. That spot turned on in a second. And it was later realized that what this was two neutron stars had collided with one another. And in addition to producing all these gravitational waves, there was a tremendous explosion that generated gamma rays. It produced what's called a gamma ray burst and a ton of electromagnetic information across the spectrum. It's fair to say that this ended up being an object that I think someone did a calculation once. 20% of people who are professional astronomers on Earth spent a fraction of their time studying this thing. If you take all the papers and you add up all the distinct authors that are on it, it boils down to, I think, 1 in every 5 astronomers on planet Earth was involved in studying this event. One of the things that's particularly cool is that by studying the spectrum of light that came at the end of this thing, we were able to solve a mystery about where the heaviest elements in the periodic table came from. We had known for years that many elements can be produced by fusion in the cores of massive stars. But when you get above iron, it's not clear exactly how you can actually produce some of those elements. One of the things that was hypothesized is that if you had two stellar cores, which are very neutron-rich, and they collide with one another, they would make exotic elements that could then decay to produce all these various things. We, in fact, showed, by studying the light from this thing, that indeed describes how many of these, all the ones that are sort of in yellow in the periodic table here, they, in fact, had to have been produced by the mergers of two neutron stars. This has a really interesting human consequence. Two very important elements for human society are gold and uranium. Let's just focus on gold. Some of you might actually have some gold jewelry. Might be wearing it right now. Every atom of gold on Earth originated in the merger of two neutron stars billions of years before our solar system formed. That's pretty cool. We've also learned that the band of gravitational waves just gets wider, okay? I've been talking about things that we've been measuring with instruments like LIGO and Virgo, where the waves are emitted at frequencies that correspond to the human ear. Well, by looking at many radio pulsars, we can actually, by sort of, these pulsars are basically very precise clocks. And so if a gravitational wave comes along, it's going to shake that clock. And so in principle, we should be able to, by monitoring many pulsars, see whether there is gravitational waves in the universe that come along and shake these things. Now, when you look at the noise characteristics, what you learn is that the best frequency band for this corresponds to sources where the periods are of order years. You need to monitor these things for many, many years in order to tease out this signal. And just about 2 years ago, this signal was finally detected. And so the particular sort of the trademark of this is that when you look at how correlated the pattern of disturbances is as a function of the angle between two pulsars in the sky, if it comes from gravitational waves, it's got to have a unique shape. And this is a great example of people just being really, really patient. Through 15 years of observation, this curve, precisely what you expect if gravitational waves are causing these pulsar clocks to jiggle, it emerged over the course of a decade and a half of observations. And what's particularly cool from the point of view of me as an astrophysicist is that the most likely source of this signal is actually massive black holes, millions or billions of solar masses at the cores of galaxies that are orbiting each other and producing this very low-frequency hum that fills all the universe. So let's look to the future. So this is the landscape that I hope we are going to be seeing in the next 10 years. LIGO continuing to operate, assuming my government doesn't do something silly. Virgo continuing to operate. GEO is a smaller scale instrument in Germany that we use as kind of a test bed for advanced technology. CAGRA is this Japanese instrument. TAMA is, again, it's kind of like a test bed for this. Years ago, the Australians had a plan for putting something together, but that's not happening. But fortunately, India has stepped up, and we are partnering with the United States to develop LIGO-India, which, if all goes well, will be operating in about 10 years. So we're hoping within the US to upgrade our instruments to something that's very large scale. So this is a Cosmic Explorer, would be sort of a LIGO-like instrument, but instead of being 4-kilometer arms, they would be 40-kilometer arms. And another instrument in India, which will be widely separated from all of these things, and by having an instrument that's very widely separated, you massively improve your ability to learn about it when you have detections from multiple instruments. And so I love this photo here with your prime minister at the signing ceremony, along with various friends of mine who I don't think, so I know over here on the left, I think he didn't realize he was going to be in a signing ceremony with the prime minister on that day. He looks a little excessively casual, but nonetheless, I think it's a wonderful highlighting of the way in which international collaboration enables amazing science to get done. We are also developing a detector that would fly in space. Okay, this is mostly being done by the European Space Agency. The US NASA agency, every now and then they say they're going to get involved, and then they change their mind, and they get back involved, and then they change their mind. And for some reason, that has a roughly 4-year cycle. But the basic idea is you sort of put 3 spacecraft in orbit around the sun, sort of trailing behind the Earth. Let me restart this video. They are individually orbiting the sun, but they're doing so in such a way that they hold a pattern that looks like an equilateral triangle that slowly rotates as it moves around in its orbit. This will have, the arms will be much longer than something like LIGO or even Cosmic Explorer. So you would sort of monitor the separation of these things using laser transponders. And the separation would be on the order of 2.5 million kilometers. That opens up the ability to hear signals at frequencies about 10,000 times lower than we measure here on Earth. That opens up the ability to probe the astrophysics of very massive objects, like the black holes that live in the cores of galaxies. I'm going to show you a little animation of one of my favorite kinds of sources. So when we look at these black holes in the cores of galaxies, we often see them sort of spark into life. And what causes that is a star that got scattered into an orbit that brings it in so close that the star is disrupted, and all this matter suddenly blasts out. And that produces what's called a tidal disruption event. We are quite sure that similar things happen where that small object that comes in is not a star, but a small black hole. Black holes can't be tidally disrupted, and so what it'll do instead is it'll orbit many, 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 many times, generating gravitational waves. And again, you can just barely hear the signal. But this will be something that many of us, and so those of you who are interested, I'll be giving a colloquium where we talk about how we model some of these things at the ICTS on Tuesday. We are developing a program to precisely compute the gravitational waves that come from these things so that we can use it to guide measurements that we would do with these things. Because these signals last for tens of thousands of orbits, we expect to be able to measure the properties of that black hole with amazing precision. So we should be able to measure the mass at sub% level accuracy, the spins at sub% level accuracy. We can even do things like say, well, suppose Einstein was wrong. Maybe there's some additional structure. Can I test how much structure beyond what general relativity predicts is present there? So this is part of a big research program that we are now all really focusing on. And that, short digression. This animation is actually a little bit out of date. It's based on a crude approximation that's surprisingly less crude than I thought it would be. It actually ends up working really well. We're in the process of upgrading it. But the animation is so old that it used to occasionally cause my laptop to reboot when it hit the last frame, because there was some kind of a memory problem that was happening. So when I put it into the slide, I forgot to update this. It doesn't happen anymore. But I would always stop it about 2 frames before the end. What you should see is this, at the end, the small black hole just plunges into the big black hole, and the signal just goes dead almost instantly. So we are at an interesting point here, where I would say gravitational wave science has reached, without a doubt, the end of the beginning. 10 years ago, that was the moment where, as I said, I was beside myself with joy. I've beside myself with ecstasy for days when I first saw that image that was on one of my colleagues' iPhones, when he basically was saying, you might want to know we've got this. That was a pretty happy day, and the month that followed was a pretty happy month. But it's now become routine. We are measuring these things on an almost daily basis, and they're turning into just sort of a tool for studying the universe. And the thing which I would like to emphasize is that it's almost like, 10 years ago, we were kind of like the first hominids who looked up at the sky and wondered, what are those bright lights up there? I wonder if there's something interesting going on. I wonder if we're connected to something bigger. This is an entirely new sense. It's akin to sound. It's not quite sound, but that's a good way to think about it. It's an entirely new sense by which we are able to explore the universe. And so my message, especially for the students who are interested in this field, our ears are open. Thank you. Now what?
Thank you, Scott, for this wonderful lecture, introducing this new way of astronomy. I hope you'll be willing to take some questions.
I'm perfectly happy to take questions, yes.
Yeah.
So.
Yes. If you have questions, I guess some of you could hand over mics, or what's your plan? Yeah.
So does someone have microphones to give to audience members?
Yes.
Who's going first? You.
Maybe, yeah, if you could raise your hands, and I can suggest some people to.
I have a question regarding. Hello, I'm here.
Oh, there you are.
Regarding gravitational waves, you mentioned that you can only measure them when you have a binary system of either black holes or neutron stars. But you also mentioned that black holes do spin. I don't know if this is a super stupid question, but are gravitational waves generated when a black hole spins by itself without any rotating bodies around it?
That's a great question. So not a stupid question. It's actually a really good question. So gravitational waves are generated when a body that has a system, I should say, that has some significant asymmetry to the mass distribution is dynamical. Binary systems are one of the strongest ways of doing that because that's about as asymmetric as you can get. Big mass here, going around each other. If I have a single black hole on its own, it actually doesn't have any asymmetry. So if it's just sitting there and it's spinning, it doesn't have any gravitational radiation that it emits. However, imagine it's not a black hole. Imagine it's a really dense star. Imagine it's a neutron star. Now, neutron stars are also probably pretty symmetric, but they may not be quite perfectly symmetric. And so one of the sources that people are trying to measure gravitational waves from right now is imagine you have a neutron star that's one of these, we now measure these things as these radio pulsars, okay? So it's got a strong magnetic field, it's spinning, and the reason that they generate radio pulses, think of the Earth, right? The Earth's got this magnetic field, it's got this sort of famous shape associated with it. Sort of field lines come out of the poles, and then they go back in, come out of the North Pole, go back into the South Pole. But the actual alignment of the field doesn't quite line up with the Earth's rotation. Pulsars apparently do the same thing. So the field lines associated with those magnetic fields are a little twisted with respect to the spin axis. And so when it whirls around on its own axis, it gets sort of the same effect. What happens is, because the magnetic fields are themselves being accelerated by this rotation, that generates these radio pulses. Okay. Now, suppose that these bodies have some lumpiness to them, or they have a shape that doesn't quite line up with the spin axis. If that's the case, it would be a gravitational wave source. Now, it would not be as strong as these binary sources. And so it's a lot harder to measure.
Right.
But people are looking.
Yeah, about the same topic, I read that. I read that when black holes spin, they also form an ellipsoid type shape. It's not perfectly spherical. So wouldn't this also count as asymmetry? It's asymmetric in this
So direction. The thing is that ellipsoidal shape to the black hole, it's aligned with the spin. So it's kind of like, imagine you take a nice sphere and you squash it.
Right.
but then you spin it in such a way that that squashed plane is exactly perpendicular to the spin axis. Okay? So there's no asymmetry associated with its movement.
Got it.
Right? Now imagine that you did that and you somehow made it wobble, then you might have something.
So recessing black holes would have gravitational waves.
They
as well.
probably, there could be a small contribution from that. And actually, that is one of the things, you know, even though my sound was a little bit of a disappointment. Oh, it was? Okay. That is one of the things that contributes to this gravitational waveform that has this additional dynamics associated with it. It's because these black holes are precessing. And I didn't get into the mathematics of what's happening here, but as part of the dynamics of the system, their spins are actually precessing as the orbit proceeds.
That's cool. I have one last question. This may be general, but since you're an astrophysicist and probably an experimental physicist.
Actually, I'm a theorist.
Oh.
Experimentalists don't like having me in their labs. I break things.
Do you have any recommendations for how to come up with good models that you can, like for example, you mentioned that you're one of the people who got awarded the Nobel Prizes. They developed a good model before they tested it actually experimentally. So do you recommend, do you have any tips about like how can we come up with such models before we just randomly experiment on something?
So what I would say is science is a very human and collaborative thing. In this case, Einstein's general theory of relativity was developed, it's one of the only examples, I think, of something which we developed almost from the power of pure thought with relatively little input from experimental data. It's, to be perfectly frank, it's a little bit of a miracle. It's held up as well as it has, okay? And we can now go back and we can take a look at that and we can understand why it is that that's the case. But it was a bit surprising. The interplay between observation and modeling and theory and refinement of a theory, going back to the data, doing a more precise measurement, that is the more standard way that science tends to get done. And as I say, it's a very human kind of endeavor. Lots of people have different kinds of expertise. You know, I sort of said that the experimentalists don't like having me in their lab because I break things. Okay, so that's just a statement of fact. I would love to be able to go into a lab and do the kind of miracles that my friends like Ray Weiss can do, but that's just not who I am. But I am really good at computer codes. I'm really good with certain kinds of mathematical calculations, so I found a niche for myself there. Everyone needs to find what that niche is that they are good at and find a community that they can apply that to.
Got it. Thank you so much.
Sir, how do you figure out the direction of the source?
How do you figure out the direction
I
of
have
the
two more
source?
questions. I'll complete all the three. Second one is, why is 1064 nanometer used in the interferometer?
Say it again.
1064 nanometer, NdArc laser. What's special about 1064?
Okay, so these are two questions about how the measurements are done.
Yeah, and the last question, if you have to bet on quantum mechanics and general theory of relativity, which would fall first? If at all, if they don't go together.
So if I was giving advice to us, let me go through your questions in order.
Yeah, sure.
So your first one was, how do I determine the direction to a source? Okay, so let's go back to my map of the Earth. So now, of course, the Earth is a sphere, okay? And so when a gravitational wave comes along, the wavefront, it comes from a source that's so far away that they behave like plane waves when they hit the Earth. So, you know, let's say they're coming from a direction where they're it's in the northern hemisphere and it's roughly over the United States. It will hit the two LIGO sites first, and they'll go through the Earth. It would hit the Virgo site. Once LIGO-India is built, it'll hit LIGO-India, and then eventually it would hit Kagra. So there's a time difference between the two of them. That time delay is a big part of how we can use to then triangulate and figure out where these things, it's not the entire thing. We can also take advantage of the fact that the arms of these antennae have a particular sensitivity pattern associated with them, okay? And so it's more sensitive to gravitational waves in some directions than from others. As it happens, when that binary neutron star was measured, the signal in Virgo was 0. That turned out to be information, because the reason it was 0 was that it was located in a place in the antenna sensitivity pattern where it was just very insensitive to gravitational waves at that position. But the absence of information in that case turned out to be really useful information, and it really helped to narrow down the position of the source in the sky, and it's why optical astronomers were able to locate it later. But in particular, because a huge contribution to this comes from timing delays, it's a good idea to have detectors widely scattered over the Earth. If you can find societies that are willing to make the contribution and they have the land space available to do that. And so that's why, on behalf of the gravitational wave community, thank you, India, for providing the facilities and the land to make this possible. In addition to, of course, the human contribution to this, a lot of the brilliant minds who are at work making this happen. You asked why 1.064 nanometers. Okay, so the question here is that when you actually do these measurements, you're making a very pure laser state. And so you have a technological choice. What kind of a laser am I going to use? If you use what's called a neodymium YAG laser, it produces light at 1.064 nanometers. Now, it turns out that from a purely engineering perspective, it's pretty easy to work with those kinds of lasers. They are very stable, they are long-lived, they have very good power consumption characteristics. And so from an engineering perspective, to be blunt, this is something that people worried about a lot. What should be the right kind of laser that we would use? And so it really was more than anything just a technical kind of question. This ends up having knock-on other technical considerations, though, because the way the mirrors are designed, if you actually look at one of the mirrors in LIGO, it doesn't look like a mirror. It looks like a piece of glass. Okay, that's because it's actually transparent to visible light, but it's very highly reflecting to 1.064 nanometers. Okay? If you were at another wavelength, you would have to design a completely different sort of mirror system. And so part of this is, just like in any good engineering system, once you've locked in a good design, it's in your interest to continue to work with it. Every now and then, someone has an idea. They say, ooh, we can do these things even better if instead of being at 1.064 nanometers, we do 532 nanometers. And then people who realize what that means in terms of all the various subsystems that need to be designed basically say, get out of the room, come back in when you're ready to behave. Because that is, it's not impossible, but it makes it difficult. Your third question, you were asking me about quantum mechanics or general relativity. Can you repeat that one again?
Like a future theory of the universe.
Yeah.
If quantum mechanics and general theory of relativity sort of don't come together eventually.
Right.
Somebody has to fall. It's going to be quantum mechanics or relativity.
Right.
Both seem to be like extremely
Here I am going to play. There's a famous quote that predictions are difficult, especially about the future. Okay, I don't know. I would say, for the benefit of the students in the audience, study everything. Okay, because you don't know all of that information is going to be useful, and it kind of comes back to what I sort of said at the beginning. Even though Newton's gravity has been superseded now, you still study Newton's gravity because even though it's a little bit incomplete, it's really good. Okay, in its domain of completeness, it describes everything. So at some point, we expect there will be some kind of a unification between general relativity and quantum mechanics. One of those things, you're right, we're going to have to change one of them. I personally suspect general relativity we will find it's probably sort of what we call a low energy approximation to some deeper kind of a theory that's very hard to access. I could be wrong, though, but that's what my gut tells me is likely to be the case. Even if that's the case, though, general relativity is still going to be the tool we use to describe orbits in our solar system, for example, and things like that. So, again, for the students, study it all. There's two here. Yeah.
I'll go back. Oh. Guys, last question before we take some YouTube questions.
I will stay to answer questions for those who don't get a chance to ask them as well. So, if that's okay with you, you're my ride. So.
So I have a question. So obviously LIGO is incredibly accurate, and one of my questions is, what have been some of the new theories that have come up based on the observations that have been made? Because,
Sorry, what happens with the...
like, what are some of the new theories that have come up about the observations that have been made? And because I'm guessing that there's a reason for deciding to build LIGO, and like what outcomes were expected out of observing these gravitational waves.
So prior to the first discovery of gravitational waves, I used to tell people that as a scientist, I wore two different hats. When I was wearing my gravity theorist hat, and I looked at gravitational waves as a science, I was interested in what we could use these measurements to maybe they will teach us about the deep structure of general relativity. Maybe they will show us that Einstein's theory is incomplete in some way. Maybe they'll show us that there's additional fields that play a role and have some kind of a coupling with things. But I would also wear what I called my astrophysicist hat. And when I was wearing my astrophysicist hat, I would say, Einstein was pretty smart. He probably got it right. What if I assume I fully understand gravity, what do I learn from these measurements? And what I learn is the properties of the stars that fill our galaxies, the most massive ones, how they evolve. I think about how I can use these as tools for measuring distances to distant events. I think about the way in which they, by combining gravitational waves with telescopes, I can learn about the formation of heavy elements. Okay, so that's what I told people up until about 2014. Then 2015 came along. Every single time we have dug in and looked at a test of general relativity, Einstein has been right. Now, that doesn't mean I'm going to stop trying to think of ways of testing it, but I won't deny that that has reduced in my priority queue my interest in sort of doing that, because, I've said it a few times, but I'll say it again. Einstein was pretty damn smart, and so he just seems to keep coming up correct over and over and over again. And that aside, what we are learning from many of these events is more about the astronomy of the sources that produce these things. We're learning about the distribution of we're learning about how stars form and evolve and how they contribute to the light from the galaxies that produce them. We're learning about the different generations of stars that produce these things. The fact that we have learned that very likely the most important source of these heavy elements is the merger of two neutron stars, that's an amazing discovery. One of my colleagues likes to point out that not only does it mean that most of our gold jewelry probably originated in a binary neutron star collision, the fact that all the uranium was likely produced in one of those things is one of the reasons why the Earth's core is as hot as it is. And the Earth's core, having the temperature that it does, is responsible for plate tectonics, which is responsible for essentially all the generations of evolution of life that we have here. So I'll be blunt, I think he's being a little bit overambitious with this statement, but he likes to claim that the merger of two neutron stars is responsible for life on Earth. Okay, that may be a little bit exaggerated, but I don't know, it's a cool thing to think about. Maybe there's something to it. So, to answer your question, I would say that it's still interesting to think about deeper theories of gravity, but gravitational waves, so far at least, are basically proving Einstein to have described everything. And so I think the interesting question is, what else can we learn with it? And I hope I kind of illustrate with this talk a lot.
Good evening, sir. You enlightened us about epicycles, that Earth was initially the center of everything, of the system, and everything revolved around it. But then it was demoted to a planet, and the sun became the center of the system.
Right.
I want to know that how did a well-settled belief turn into a doubt and then basically be concluded as a false information? What was it about the change, the gravitational wave, or the space that made Copernicus believe that sun was the center, not the Earth?
So that's an excellent question. And it's one that I fear I'm not going to be able to really answer, because I suspect the answer is more in the realm of psychology than in physics. I mean, I think Copernicus was the first one to have suggested perhaps the Earth is not at the center. Let's put the sun at the center. This was an early application of what we have come to call Occam's razor. Occam's razor tells us that if you have multiple explanations for a phenomenon, the most likely explanation is the simplest. So Copernicus noted that you could get rid of these epicycles if the Earth was not at the center, but if the Earth was moving at its own orbit around the sun. And so I think he was probably just motivated by simplicity. Can I make a model that is simpler than this? And where this gets into psychology and really theology is that this contradicted the dogma of the time that the Earth was the center of the universe. And it's one of the reasons why it was as controversial as it was. But at the end of the day, I suspect it was, if you just take a purely pragmatic, data-driven explanation, it allowed you to describe the data with what looked like a much simpler picture than what the epicycles did. But then again, Copernicus has been dead for over 500 years, so I'm speculating a little bit.
Excuse me. Here. Sir?
Yes, where's the...
Here. All the way here.
Hi.
I had a doubt regarding the measurement of the black hole waves. So we know that gravity can't travel faster than light, right?
Gravity, so disturbances to gravity, to the best of our ability to measure it, travel at the same speed as light travels.
Okay. So the data that LIGO is measuring, it's from black holes really far away.
Yes.
So the events that are they happening in real time, or have they happened multiple years before and we're getting to know them now?
So strictly speaking, we would say that these are events that occurred. So for instance, the very first event that LIGO measured is estimated to have been, so the actual distance to the event's a little bit not measured that precisely, but it was about 3 billion light years away. So we would say that signal has been traveling to Earth. Those black holes collided 3 billion years ago and have been traveling to us ever since. Having said that, though, it's worth remembering that we always measure everything using information that travels at the speed of light, okay? So from our perspective, we can only see things that are sort of happening, that travel to us by light. So for us, it's happening right now. Right? In the same way that, you are seeing me, so you are about, let's say, about 50 meters away from me. So there's a time lag between the light bouncing off of me and getting to you. So that is sort of built into things there, right? We kind of build that in. It's easy to do on a human scale. It's harder to do when the distance scales are billions of light years. But nonetheless, I think the same concept applies.
Thank you so much. That was
Sure. You've had your hand up patiently many times. Yes, I'm glad you got the microphone.
So I realize this might be in the area of speculation because the Earth is a point in the entire universe on a cosmic scale. So the question is, what do you speculate would be the shape of the gravitational wave front as it expands from the event horizon, from the place where the event actually occurred? Would it be a perfect sphere?
So the gravitational wave, when it's generated from its source, it sort of is a sphere, but certain angles are stronger than others. And this is actually one of the ways that we can take advantage of that fact in our detailed analysis, because one thing which I didn't discuss here is that gravitational waves come in what we call two different polarizations. So there's one, so if I have a detector that has arms like this, there's a polarization such that this sort of lines up perfectly. But there's another polarization that is orthogonal to this, which that detector would miss. I can set up a second detector. That detector would be perfectly aligned to catch the other polarization, but miss the first one. The angular behavior of this sort of so when I look at gravitational waves generated from a source, they kind of move out on spheres, but they're stronger in some angles than they are at others. And the detailed variation of that angular behavior is different for those two polarizations. And so by measuring both of those two polarizations and comparing their strengths, I can actually use that to figure out which angle the source was actually oriented at when I measure it. So, you're right, the Earth is effectively a point to something that's this far away. But when I get in and I actually measure this thing, the fact that the gravitational wave is acting on a relatively, on human scales, a large length, is something that I can use to tease out this kind of information.
Okay. And one follow-up question. Is there anything that you think might interfere with the propagation of the gravitational wave, like when it passes through a galaxy
Right.
or through a gas giant, or let's say Uranus or Jupiter were directly in the path of that gravitational wave as it approached the Earth? Would it have an effect?
That's a great question. So what you're asking me essentially is, can anything scatter the gravitational wave? Like, if I take light, air is transparent to light, but wood is not, right? So, my laser beam goes happily across the room, and then it sort of stops on the wood. Is there anything like wood? Is there anything that can stop a gravitational wave like that? Physicists characterize the fundamental forces by how strong they are. And it turns out gravity is the weakest of all of them. And what that means is that in order for matter to significantly scatter or have an influence on a gravitational wave, it would have to be so massive and so dense that it would actually collapse into a black hole. So basically the answer to your question is nothing is going to scatter it in the same way that you do with light. And indeed, that's one of the reasons why these things are so hard to measure, because we actually do want them to scatter and interact with our instruments. But this is why we have an event that, if it had been light, would have been as bright as 175 billion Milky Way galaxies, but instead it just moved these little mirrors by a fraction of an atomic nucleus size. That's kind of what goes on here. So if it propagates, let's say this is occurring 3 billion light years away, it probably passed through 100,000 galaxies en route to us, and they had barely any effect on it that we can measure. One thing which they can do is, famously, light bends in the presence of a gravitational field. That causes what's called lensing effects. So gravity can act like a lens. That will happen not just to light, that will happen to gravitational waves. And so a really interesting question is, can we detect the influence of gravitational lensing on gravitational waves? And actually, I know there's some people at ICTS who are thinking about that very question. It's a little bit tricky because you don't have images, but you kind of think of this sound-like analogy. It would be kind of like you would hear your signal, and then if it was lensed, you might hear it again, but slightly quieter or louder. So that's the kind of thing you would look for.
So, right here in the back. Yes, sir. So my question is, it has to do with black holes.
One second. So this is the last question, guys. We'll have Heidi after this. I mean, you guys, if you have any questions, you can ask there. So don't worry about it. Yeah, you can.
Yeah. So growing up all over the internet, I saw many interpretations of the black hole, visually speaking.
Yeah.
So, but a couple of years ago, I think the first picture of a black hole from Messier 87 came out. And what really intrigued me was, I don't know if this question has much to do with gravitational waves, but my question is, I see an accretion disk around the singularity of the black hole.
Yeah. It's actually around the event horizon.
Right, event horizon. And
Important distinction.
what intrigues me is why, if the black hole is so dense and pulls almost anything around its vicinity into the singularity to become one with the singularity, why is the accretion disk still there? Why is it rotating around the black hole?
Because it's orbiting. Okay, so suppose right now, I seem to have lost my sound. Suppose right now our sun collapsed into a black hole. Okay? So first of all, an ice age would start pretty quickly, but let's ignore that for a second. What would happen to the orbits of the planets around it? The answer is absolutely nothing. Our solar system would continue to orbit around that black hole essentially forever. So the thing is, a black hole doesn't just suck everything into it. It's just a strong source of gravity. Okay? And so if you're away from that event horizon, if you're not actually touching the event horizon, you can form an orbit around that thing and you can orbit it forever. And that's what the accreting matter is doing. It's just matter that is on an orbit. Okay? It's probably not a very happy orbit for any living being that happens to be there, but in principle, someone can go onto that orbit and sit basically forever.
Okay, that answers my question. Thank you. Have a great day.
Yes. Yeah, I can talk more about that afterwards. All right, where do we stand?
Looks like we have to close this very interesting Q&A session, but Scott will be here for another 20 minutes or so at the coffee, so you're welcome to hold him for more questions. Let me thank everyone, and in particular Scott, for giving this wonderful lecture and interacting with all of you. On behalf of ICTS, let me also thank Scott and PES for co-organizing this event. As a small token of our appreciation, let me hand over a small memento.
Thank you very much. Thank you.
Sometimes I feel occupying positions, administrative positions, is a big no-no. I hardly got to listen to even 5 minutes of the talk because I'm the Dean of Student Affairs. I don't know why affairs. Okay, I'm sure you all enjoyed it. Thanks to the International Center for Theoretical Sciences for making this engrossing event possible. And a big shout out to Team Q Forest. Quickly, can I have the names of the heads? Karthik, shout out. Yes? Manya, Kenny, Saira. Right. Thank you. But I think the biggest shout out is for the professor who came from Massachusetts Institute of Technology, from the US of A, in spite of a lot of hiccups here and there, and with the president of USA making things very difficult for everyone. We still have him here. Thank you so much, Scott.
Thank you.
The Dean of the International Center for Theoretical Sciences, Dr. Ajit Parameswaran, a big name by himself. His own Einstein Lectures on astrophysics have been legion. Thank you so much, Dr. Ajit, for your kind presence here. I request Dr. S. Radhakrishnan, the chairperson of the physics department of the Science and Humanities Wing, to kindly honor Dr. Ajit.
Good evening, everybody. It was quite an exciting talk from Professor Scott. We have been quite lucky with ICTS because I think 2017 or 16, we had professors from ICTS, Shubhro Bhattacharjee, who came as our external expert for our syllabus committee. And since then, we have been pushing this quantum agenda in a big way. We are aspiring to be a quantum computing lead in the country. And yes, it all started with very healthy inputs from ICTS professors. We had visited them. And we already have heard Ajit sir giving talks in our own institution. So it is quite nice that we are rebuilding this association. And sir, we will be open to any such events jointly, say, conducted between ICTS and PES. We will be open to such invitations. Thank you.